So, hello everyone, we will continue our discussion on CTL in this class. If you remember, in the last class we introduced CTL and you have taken certain property and then explain what is their interpretation, but we have not formally defined the semantics of CTL, right. So, in today's class quickly we will discuss define the syntax and semantics of CTL. So, syntax I have already introduced in the last class, so I will quickly conclude is the meaning or what is the correct way of writing CTL formula, you have to follow this. So, any propositions, is atomic propositions are CTL formula. If there are two CTL formula phi and psi, its negation, their conjunction, their disjunction and their implications are CTL formula. Similarly, this I have also discussed in the last class. The temporal operators are bind closely with the path operator, right. So, you have temporal operator x, g, f and u, this is the temporal operator, and you have path operator or path quantifier a and e, right. A is all path and E is their existing path. So, you have all 8 combinations, right, and this I have defined very precisely in the previous class. So, here just quickly summarize, it is basically saying that in all path in next state p holes, there exists a path in which next state p holes. This is in all path in future p holes, there exists a path where in future p holes, and this is in all path in all state p holes, globally p holes, e.g. there exists a path in which in every state p holes, and this is in all path p holes until q holes, and this is there exists a path in which p holes until q holes. And you remember, everything is basically defined over a branching tree, not only one path. Okay. So, syntax is clear. This precedence is important in CTL formula, because if you write a formula where you do not put the parenthesis, it will go by this. So, this precedence going in this order, the highest precedence is on negation, then the temporal operator x, f and g, so they get the highest priority, then the binary operator and or, followed by implication a u and u, right. So, if you write a property like say a implies b or c, it means this, because it has higher precedence, right. Similarly, if you write a, say a f p until say e g q, right, this is a valid property, right, because this is a property and then I am quantifying the path quantifier. So, AFP is a valid CTL property, EGP is a valid CTL property, EGQ, and their until is also, right. Now, if you see here, you have AFP. So, here because this AF has higher priority, so it is effectively means this until this and then this parenthesis, right. So, ideally we use parenthesis for avoid all this confusion, but if you do not use this, this will be the priority or the precedence. And you also have to remember the associativity. So, if you write A and B or C, it is left associative, right. So, it is basically mean then, and if you write A implies B implies C, it is right associative, it means this. Okay, you have to just remember this, but I will strongly suggest you to parenthesize, so that you do not rely on the tool. Okay. So, I will now formally define the semantics. Again, semantics we have mostly discussed informally in the previous class with examples. Semantics means meaning, right. When you write a property, what does it effectively mean, right. So, as I mentioned here, whenever you define the semantics, you basically take a state machine, Kripke structure or transition system. In that we already defined in LTL cases also. So, it has set of states. So, that transition system has set of states, set of transitions, right, and the level for every state with the atomic propositions, and you have S0 is the start state. Okay. So, you have this. So, you will define this formula on context of this transition system, and if you remember, for LTL we just take one path on this transition system and defines everything. Here I will take a branch, right, or a tree, and I will define that. meaning of the formula on that tree. Okay. And you already know that there are two path quantifier E and A. A means for all paths starting from the state S0, and E phi means there exists one path starting from the S which satisfy this. So, this we have already discussed many times. With this, now let us define the semantics of CTL. So, what we are writing here, that if you have a transition system and you have say S is the start state and phi is the CTL formula. So, I will say that this start state M of S satisfy phi, that means the state S in the model. S can be any state, but usually if I say the model satisfy the property, that means the start state satisfy this. Okay. But you can always say some other state also satisfying some property, but to model satisfy this, you have to check for the start state. And then I will define what is the meaning of all combinations that we have defined in this case, right. So, I will define the exact meaning of this formally and exact meaning of this formally now. Okay. So, if I have atomic proposition P and if I say that MS satisfy means MS satisfy P means that particular state level should be P, right. So, you have if S level is P, then I will say that that particular state satisfy P, right. This is obvious. And the negation, I will say that MS satisfy negation of phi if M of that S does not satisfy phi. So, then it is satisfying the negation of the property. Okay. Conjunction, if that model satisfy phi 1 and phi 2, if and only if it is individually satisfy phi 1 and individually satisfy phi 2. So, if individually getting satisfied, then I will say their conjunction is also getting satisfied. Similarly, I am saying that if the model satisfying phi 1 or phi 2, if and only if it satisfies phi 1 or phi 2. Similarly, for implications. For next, we have already defined that if this is getting satisfied, that means there exists a S which is basically a transition, right, S to S dash. That means S dash is a next state of S, and in the next state phi satisfied, right. So, this is we have already discussed. Let us say I have a branching tree like this, and in this state phi holds, then this is my S dash, this is S, then I will say this M S satisfy E x phi, right. This is formally. A x phi means in for all path in next state phi holds, that means for all such S dash, right. So, it has two next states. So, this is also S state which is basically the next state of S, and both cases phi holds, here also phi holds, right. In this case, I will write M S satisfy A x phi, right. If you attend my previous class, it is very easy to understood, right. Similarly, E g phi is basically saying there exists a path which is of the form say S0, S1, S2 and so on. In this path, in all I, this phi satisfies, right. So, M Si satisfy phi, which is something like this, right. Let us say I have this is the path in which phi holds here, phi holds here, phi holds here. That means this is my S0, this is S1, S2 and so on. In this path phi always hold. So, I will say in this path this is hold. So, I will say MS satisfy S satisfy EG phi. So, here S0 means the start state. Similarly, AG phi means in all paths starting from the start state, in all state satisfy phi. Effectively means in all state phi should hold, right. Then only this is true. So, that means in all path starting from that S, in all state this phi should hold. Okay. And this EF phi, that means there exists a path starting from S, and in this path in future there exists a state I in which phi holds. It is not in all state. So, the difference here it is for all state Si holds here, for Eg because it is globally holds, here Ef, that means in some future state it holds. So, there exists some state I such that MSI holds phi, right. So, this is very much clear. If you have a tree like this right. So, let us say I have this is my path, right. In path there is some future state where say phi holds here. So, then I will say this M S satisfy E F phi, and this means in all path in future, that means for all path starting from of the form say S, S1, S2, S3 and so on, there exists I such that Si holds. So, that means for this path also it should hold, for this path should also hold, let us say phi holds here, for this path also it should hold, let us say phi holds here, for this path also it should hold, phi holds. Then I will write M S satisfy A F phi. Okay, clear? Similarly, the until E until phi 1 and phi 2 means there exists a path starting from S such that there exists some I in this path where phi 2 holds, and for all j less than I, Sj holds phi 1. So, this is the standard definition of phi 1 and phi 2, and this is happening for one path. There exists at least one path, right, and for all it is basically for all path this is happening, right. So, for all path this is the case where there exists some I in that path where in that state phi 2 holds and all previous state phi 1 holds, right. So, this is well understood. Okay. So, syntax we understood. So, now I will take a small example and I will ask you effectively questions whether this holds or not, right. So, let us say I have this case, right, and this is basically infinite. In this case, does exp holds from this state? Yes, because there is a next state where p holds. So, this is true, right. Then is efp holds? Yes, because if exp holds, that efp also holds, right. There exists a path in which future p holds, right. So, this is also hold. Is egp holds here? Should be there should be a path in which globally p holds, and again this is true because you see this path, this is an infinite path in which p holds here, p holds here, p holds here. So, this is also true, right. Now, if I say agp, that means in all path globally p holds, it is not, right, because I found this path in which p does not hold here, I found another path here where p does not hold here, does not hold here. So, this does not hold. So, that means agp does not hold in this model. Okay. Now, how do you get this, right? This is just a tree which you obtain, as I mentioned, from some state machine. So, let us try to see that how we are getting this. So, this is one FSM which I say let us say I have obtained from some design and in which I want to check certain property. Okay. So, I will just kind of unroll this model to get this tree. Let us say I have S0 here. From S0 you can go S1 and S2, right, because you have transition here and here, right. So, there will be two next state S1 and S2. Now, from S1 you can go to S0 or S2, right. So, from here you have S0 and S2. From S2 you can only go to S2. So, it has, so basically this will now loop here, right, S2, 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 and from S0 again you will go to S1 and S2, right, and S2 will loop forever, right. So, again from S2 it will loop forever, from S1 you will get S0 and S2, right, and S2 will loop forever and this will continue like this. So, this is the kind of tree you will get for this behavior. Okay. Now, I will want to check. So, here I can just put the, so it has in S0 PQ holds, in S1 Q and R holds, and in S2 R holds. So, this way I can just put the proposition here, right, S2 R holds, S1 Q and R holds, S2 R holds, here PQ holds, here R holds and so on, right. So, this is the kind of things I am going to get. Now, I am checking whether this S0 satisfy P and Q, which is true because P and Q both holds here. So, this is true, right. Then if I say S0 satisfy not of R, yes, because R does not occur here, that means not of R occurs. So, this is also true because M S0 does not satisfy R, it means it satisfies not R, right. Now, if I try to check this Ex, Q and R, so I am going to check Ex, Q and R. Again it is from S0, I am going to check this. So, I want to get a next state in which Q and R both hold, right, Q and R. So, which is basically happening here, if you come to this state, Q and R both holds, right. So, there exists a next state, there exists a path in which next state this holds. So, then I can say that this is true, right. So, now rest of the things I can discuss here also. So, I am trying to say that in all path next state P and R holds. So, if you think about starting from here, in this state P R does not hold, right, and in this case also P and R does not hold, and I am taking a negation of that, right. So, that means this is also hold, because effectively M S0 does not satisfy A X P and R. That means in all path next state P and R holds. If you see here, in this state also P and R both does not hold, here also P and R does not hold, right. So, effectively this does not satisfy this. So, that means it satisfies the negation of that formula, right. It satisfies negation of A X P and R. Now, I am trying to see there exists a path in which future P and R holds, P and R holds, right. So, you see here because there is no state where P and R holds, so I will not able to get anything, right. So, if I think about this one, so if you go through this path, no path where P and R holds, if you go through this path, no state where P and R both holds, so on in all cases, right. So, I will say that this does not satisfy, right. So, effectively M S0 does not satisfy, there exists a future state where both P and R holds. Now, I am trying to see there exists a path in which G globally true, right, G in globally R true, that means globally R holds. So, if you see here there exists a path in which, so if you think about, so here R does not hold, right. So, this is also not true effectively. If you think about here, you basically have to have a path where P R true, but any path starting from S0 here R does not hold, right. So, no matter I have to check anything, if you take any path, the first state itself does not hold, right. So, effectively in this case, this model M S0 does not satisfy E G R, right, or E G R. It means there does not exist any path in which globally R holds, all other state R holds except S0. So, if you think about this path, here R holds, but R does not hold here. So, it does not matter, right. So, if you start from here, you think about this path, here R holds, here R holds, but in the start state itself R does not hold. So, this is not true, right. So, this does not hold. Let me take a little bit complex one now. Here I am just checking all path in future R holds, which is true, right. So, I am starting from here, I come here, R holds, from here I come here, R holds, right. So, that means after that I do not need to check anything, right. So, this is true. If you go back here, from here R holds here, R holds here. So, in all path in future R holds, right. So, then this is true, right. Now, think about this. Let me just draw this one more time. So, you have S0, then you have S1 and S2 loops here P and Q, this is R, S1 is Q and R, in S1 I can go back to S0 or I go to S2 again loop, from S0 I will get to S1 and S2 will loop, and from S1 again I will go to S0 and S2 and so on, right, because this will keep repeating, right, P and Q, this is R, this is Q and R, okay, and so on. So, now here I am going to check there exists a path in which P and Q holds until R holds, okay. You see carefully. So, here P and Q holds, right. So, here P and Q holds until R holds, here R holds, here R holds. Basically, I found that in all path P and Q holds until R holds. So, then I will say that this M S0 satisfy A, P and Q holds until R holds, because I found S1 and S2 both cases R holds and P and Q holds in S0 itself. So, that means all paths starting from S0 this would hold. So, this is true, right, and this is E and both cases, because E, P until Q also hold, because it is hold A, it is for hold for A also, right, because in this case also here also R holds, here also R holds. So, it is whole M S0 holds A, P and Q until R. Obviously, this should also satisfy E, P and Q until R, right. So, this is okay. Then I am checking in all path P until R holds. So, P holds here, R holds here, P holds here, R holds here. So, obviously, this is also true, right. So, I will say that M S0 satisfy A, P until R. The last one little bit complicated. So, what I am written AG, if this hold P or Q or R holds, implies EF, EG, R holds, right. So, this part is understood, that means in all path globally, right. So, in all path in all state, if P or Q or R holds in that state, implies from that state there exists a path in which in future this should hold, right. There exists a path in future where EGR holds. What is EGR? EGR means there exists a path in which globally R holds, right. So, let us try to see this. So, since here in any state R S2, because S2 is the kind of a infinite loop here, right. So, I can write that EGR holds here, right, because if I start from this state, it will be only S2, 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 S2. So, there exists a path in which globally R holds, right. So, any state S2 where EGR holds, right. So, all this S2 EGR holds, right, EGR, 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 right. Now, what I am saying here is that in all path globally P, Q, R holds. If you see here, either P holds, Q holds or R holds. So, if you think about all state, either P holds, Q holds or R holds. So, this is basically true for all state here, right. So, I have to check this in all state. So, that means in all state this should satisfy, right. What is this? I am saying that from all state there exists a path in which future EGR holds, right. So, now let us think about this state. From this state there exists a path where EGR holds. From this state there exists a path where EGR holds. From this state there exists a path in which in future EGR holds. From this state again I have a path where EGR holds, and from S2 also is keep going on, right. So, that means this property is true in this model, right. So, here I am able to reach from every state there exists a path in future I got EGR holds, right. So, which is happening here. So, this is very interesting example, and so that this particular actually holds in this particular example. Okay. So, I think that is all for today's class. So, what we have learned today? We have formally learned the syntax and semantics of CTL, and we have taken a state machine and we have seen various example and check whether those particular property is true in that particular state machine or not. Okay. Thank you.